All right, let's talk about section 8.8, vectors. So the very first thing that we want to talk about is the definition of what a vector actually is. So a vector, it says here, is a quantity defined by its magnitude, which is just a fancy word for its length, and a direction. So a vector has magnitude and direction. It begins at an initial point, that is where it starts, and it ends at a terminal point, that is where it terminates. There's three things about vectors that you just need to know, and it's not too complicated. And I'll draw an example before we get done with this. 1. We write a vector in lowercase boldface typed, or we use an arrow on top if bold is difficult. So it's actually difficult for us to do a bold V. If I wanted to do a bold V, I guess I'd have to do something like this. And that doesn't necessarily look great, so instead I would just do something like that. That's enough for a V. And notice how I don't actually complete the arrow. That's pretty common to do it like that. You could also write an arrow with the arrow part on top. Any of these are vector V. This, however, would just be a variable. All right. The second thing is given an initial point A and a terminal point B. We may also write a vector as vector AB is how that's written. This is also read as vector V, vector U, vector W, and then again vector V, vector U, vector W. And then given an initial point at the origin, 0, 0, and terminal point AB, we may write the vector as, and then we use these special braces, AB. And all that means is that it goes to AB from the origin, and we'll talk about that more later. But for now, I just want you to think of a vector. And a vector is really just going to look like a ray. If I don't actually draw a grid, that's a vector. The vector has some point that we start at. So if I draw like the Cartesian coordinate system, it has some point that we start at. So you go over A and up B, for example. And then you'll end at some other point up here. We'll call that X comma Y, for example, if you want, and that would be your vector. So your vector has a magnitude, that is the length of this line here, and a direction. It's going, well, this way. And we'll talk more about that as we move on. But basically, a vector is just a construct or a quantity that has magnitude and direction. And I've said it multiple times because it's something I'd like you to remember. So let's talk about standard position a little bit more. It's that third point. So talking about standard position here, the standard position of a vector has initial point 0, 0. That is the standard position vector is going to start at the origin. So if that vector has terminal point, that is, it ends at AB, then we write the vector as AB, and we just read this as vector A, B. So it has these braces, though. So they're sharp, sort of pointy, basically greater than or less than signs that are drawn a little more lazily. The actual greater than, less than signs are usually drawn like that. We normally draw our points like this. But if you do come in here and you do something like this, that's good enough while you're writing. Any vector written like this here, with these braces, is assumed to start at the origin and terminate at the point AB. And that's the most important thing. If you see it written like this, then it starts at the origin, 0, 0. And it terminates at AB. The position vector for any vector with initial point x1, y1, and terminal point x2, y2 is, you just subtract the points. And I'll show you what that looks like. So given a vector with initial point 4, 5 and terminal point 7, 10, we want to find its position vector and show graphically what has been done. So we're just going to do the math mindlessly first, and then I'm going to show you how this works. So we know that we start at your initial point 4, 5, so on the coordinate grid, and we know that we terminate, so our terminal point where we end at is 7, 10. So then I know that its position vector, its standard position vector, is going to be exactly, okay, take the terminal point, which is 7 for the x, and subtract from it the 4 in the x position up here. I did where you ended minus where you started in the x direction, and then I do the same thing for the y, where you ended, where you started here. 10 minus 5, Okay, and then we say that that equals, and then just do the math on each part. So 7 minus 4 is 3, and 10 minus 5 is 5. Okay, so 3, 5 is the vector that we're talking about. All right, so let's think about that for just a second. So as we think about this, let's draw a little Cartesian coordinate system here. I can do it in white, just a little one. We don't have to think about it too much. And I'm actually going to make the entire thing be the first quadrant, since everything here is in the first quadrant. And then I'm going to come in and I'm going to label our initial point 4, 5. So I need to come over 4. So 1, 2, 3, 4 we'll say, and then up 5, 1, 2, 3, 4, 5. This isn't exactly to scale, but there's our initial point, and we called it A. So there's our initial point A. Okay, and then our terminal point was 7, 10. So there's 4, 5, 6, 7, and then we've already went up 1, 2, 3, 4, 5. So let's go up 6, 7, 8, 9, 10. So here is our terminal point B, and our vector here in yellow is the straight line that goes directly in between these. So just like this, and it has this direction. So that's the vector that we've got. Now I'm also going to go ahead and plot the standard position vector 3, 5, which means we start down here, and then we go to the right 3 and up 5, and that's the terminal point. So I'm going to do that also in orange. So to the right 3 and up 5, so up 1, 2, 3, 4, 5, to right here. And then I'm going to do this one in blue. And let's do this exact same thing. And hopefully, if everything is drawn to scale nicely, which it is, close enough, you'll see that these two vectors are exactly the same. All that we've done is just moved this orange one down here to this blue one. So that's all that's been done graphically. That's what I meant by that part. So all that we're doing is we're just taking this guy here and saying, okay, let's just move you down so that you start at the origin, buddy. And it's the exact same sort of thing. So keep in mind that all you do when you want to figure out, you're given some terminal point like this and initial point like this, where the initial point isn't at the origin, you can move it to the origin by just doing this here, which is take the terminal point, the terminal point's x coordinate, and subtract the initial point's x coordinate, and do the same thing for its y coordinates. And that's all that there is to it. So you'll take this in the terminal minus this in the initial, that's your new x. Take this in the terminal, this in the initial, that's your new y. And what you're going to get out is the terminal point of a vector that starts at the origin. And that's all that there is to that. And if that seems too complicated, we'll do some practice with them in class, and you'll see what's going on. All right, so now let's add vectors together. So given two vectors, v1 and v2, and notice that they're both in standard position, adding them is as simple as adding their components. So here we are given vectors v1, 3, 4, and v2 is 1, 5. We're asked to find v1 plus v2, and then we're going to use the graph to deduce the method graphically. So I'm going to show you what we're doing graphically as well, and it's actually pretty cool what this means. But we're just going to go ahead and add these two things together. I want to know what v1 plus v2 is, okay? And these are vectors, so let's put little hats on them. And that's just going to be, well, we just add together the x's, so 3 plus 1. And then we're just going to add together the y's, so 4 plus 5. And we're going to get that that is very clearly 4, 9. So that's the vector 4, 9. Okay? And let's keep that in mind. So I'm going to write down here that we had the vectors 3, 4, okay, and we added to it the vector 1, 5, like this, and we got the vector 4, 9. And I'm just going to write that down there so that when we scroll down in a second and look at that, we can understand. But again, to add the two components, you just add the x's together and you add the y's together. Now that's not even the cool part. The cool part is what this actually does on the graph. But keep in mind that these things are in standard position. That means that they start at the origin. That's what these things here mean. When you see something in there, it means not only is it a vector, but it starts at 0, 0. Anytime that you see these braces like this on your thing, you know that you start at 0, 0 and you end. Your terminal point is given to you here. You start at 0, 0 always when you're using these braces. You end at, for this one, 4, 9. So let me show you that on a graph. So we've got the graph here, and I want to do 3, 4, 1, 5, and 4, 9. And I'm just going to take full advantage of color here. So we're going to do 3, 4 in this nice blue. We'll do 1, 5 in this nice orangish color. And then I'll go ahead and do 4, 9, like actually in red. So let me show you all three of these. And this should be a really cool example of how this works. So let's go into this. So graphing 3, 4, we're going to start at the origin. So let's just start at the origin here. And we're going to go over 3 and up 4, right like this. And we're going to stop. Okay, this is so cool. All right, and I'm going to draw the head of this on here. Then I'm going to switch over to my other color here, and we're going to do 1, 5. So I start again at the origin, and I go over 1 and up 5, and I draw it there, and that is the vector 1, 5, or at least very close, okay? And then we're also going to do the vector 4, 9. So I start at the origin as best I can, and I go over 4 and up 9, and I'm going to show you what happens. So remember, red is your resultant vector. Let me try that again. Let's go over to 4, 9. There we go. I'm going to put the head on that thing. Now watch this. What this means graphically is your choice. It doesn't matter which one you do. But if you come over here and you select this vector here, and if you drag it so that its tail, where it starts, is at the, its head rather, where it starts, is at where the other vector ends, it's the exact same thing. So I just picked the thing up and I moved it up here, and that right there is what we mean when we say that, that this vector here, this blue vector here, plus this red vector here, plus this orange vector here, rather, is the same thing as the red vector. It goes the exact same distance. And the really cool thing about it is it doesn't matter which way you do it. You can also just go ahead and grab the blue vector here, and if you move it like this, you'll notice that it still makes it to the exact same point. And I think that that's just amazing, that you have this graphical intuition that all that you're doing is just dragging these things around. And it's this idea that if I go to 3, 4 and then to 1, 5 in that sort of way that we did it, that this roundabout way is the same thing as just going straight between the 2 points. That is what adding them does. It just puts one of them at the end of the other, and it doesn't matter which way that you do it. And I think that that's just the coolest thing. So that's what it means when you add two vectors together. That's just called the head to tail method of adding, and you'll get plenty of practice with that, don't worry. So keep that in your head. I think that that's awesome. Let's move on. So now we're given vector A is -2, 3, and B is -1, -2. We want to find A plus B and use the graph to graph it. So you all should be able to actually do this on your own very easily. And I'm just going to go ahead and write this out real quick. But we know that vector A plus vector B is just going to be, well, it's going to be -2 plus -1, okay, which is -3. And then 3 plus -2, which is -1. Or +1, rather. +1. Okay, that's it. Be careful with signs there. And if you want to know where each one of those parts came from, I challenge you to scroll back up and look at how we did the last example. But that's where those numbers came from. It was just I put together -2 and +1. So I added them together. So -2 plus +1 is -3. And then 3 plus -2 is +1. And then we're going to figure out what it is that we talked about. So what we did was we put together -2, 3, Okay, and we added to it -1, -2. And I'm just writing this so that I still have the problem when I scroll down. And what we got was -3, 1. And you should know exactly what's about to happen. So I'm going to graph this one in blue. I'm going to graph this one in red. And I'm going to graph this one in orange. And I'll show you what that looks like. All right. So let's graph -2, 3, and I'll show you what we're doing. So -2, 3 is start as close to the origin as you can. There we go. -2, 3 is about that vector right there. Okay, and I'll draw the head on that. -1, -2 was the other thing that we did. So -1, -2, -1, -2 is this vector right here. And remember, these are all standard position vectors, so we're starting at 0, 0, and I know that because of what I used right here. And then I'm going to graph -3, 1. So I want to get it as exactly as I can. So -3, 1, right like that. -3, 1, exactly like that. There we go. There we go. And now watch this. If you take any one of these, either one of the original vectors, either the orange vector or the red vector, and you drag it so that it begins where the other one ends, you're going to end up in exactly the same place. So there's one way, and here is the other way. And I just think that that's amazing, there's such a nice graphical intuition for how vectors work. So that is the head-to-tail method of how to do that, and again, we'll get plenty of practice on that. But that is graphically what you're doing, and it doesn't matter which way you do it. They're both equally valid. Just make sure to never move the vector, this vector here, your blue vector, the actual resultant vector that you got when you added it together. That's not one of the ones that gets to be manipulated. But the other two, you move one so that it begins where the other one ends, and you will always end up at the same terminal point as your resultant vector. The resultant vector being the vector you got as a result of adding together the other two vectors. So now we're going to talk about scalar multiplication. And a scalar is just a constant that's dealt with out front. So given c being some real number and some vector in standard unit position, x1, y1, like this, then c times the vector is the same thing. So multiplying your scalar times the vector is the same thing as multiplying the scalar times each of the components. So we have vector q being 6, 2. We want to find 2 vector q, -2 vector q, -1/3 vector q, and pi vector q. And we want to explain graphically. Now I'm not going to go over all of those graphically. I'll just go over the first 3. Pi q is going to be kind of difficult to do, but we can look at all of these really quickly and just do the math on them. None of those are difficult to think about. And I'm going to write them all down here. So we're going to write down here that our vector q is 6, 2. Okay, and then we're going to find all of these. So 2 times vector q, 2 times vector q is going to be multiply each one of those things by 2. So it's going to be 12 times, it's going to be 6 times 2, which is 12, 2 times 2, which is 4. Okay. And then you make sure to finish it off with a thing like this, -2 vector q is going to be -12, -4. I multiply each part by a negative. Awesome. -1/3 q is I multiply each part by a -1/3. So I get that -1/3 times vector q is equal to the vector -1/3 times 6. So 1/3 of 6 is 2. And make it negative, so -2, and then negative, well, 2/3. That's what -1/3 times 2 is. It's -2/3. Put your stuff in there and you're done. And then, of course, the one that I'm not actually going to graph, but I'll show you, pi times vector q is multiply both parts by pi. So 6 pi, 2 pi. That's a vector with terminal point at 6 times pi, whatever that is, 2 times pi, whatever that is. So those are all the things, and then we just want to explain it graphically. And it's going to be useful to actually show you the original vector versus some of the other vectors, which will be kind of difficult because we only go to 10, but we'll see what it looks like. So if we wanted to graph vector q, which I'll do in this original blue, vector q is 6, 2. Now it's written in standard position, and I know that because it uses those little angle braces. So it starts right here at the origin. They all start at the origin if they're written like that. And it goes over 6 and then up 2. So vector q is this vector right here. That's the vector. Okay, that is vector q. And then I want to look at vector 2q. So vector 2q goes to 12, 4. And so if we're very exact with that, if we're very exact with this and we think about it, we can actually extend this a little bit if we need to. Okay, and we can put in roughly, that looks like about 11, and this looks like about 12. Okay, and this is how you do it if you didn't have enough space on a test or whatever to do it. But I want to then get 2q, which was 12, 4, and I'm going to do this in red. So 2q is 12, 4. So 12, 4 is come all the way over here. So starting here. And if I did this right, I should come up to 4. And yeah, 12, 4 is about right there, roughly. So 12, 4. Let me get this as exact as I can. So 12, 4 is about right there. And you should notice that what we did was we just doubled the length of the vector in the same direction. So we have this down here, this distance here is q. This down here is once again q. It's the exact same distance. And if you want to figure out that distance, it's as simple as using the Pythagorean theorem here. You just drop this and you know all these distances, and you can drop this and you know all these distances, and you can start doing stuff with it. But this length is indeed the same thing as this length. That is, this entire thing's length, that is 2q, is exactly twice the length of the original vector q. That's q, this is 2q. And I think that that's really cool. So all that a scalar multiplication by a positive number does is it just stretches the vector. Now you could think of 1/2 q. If you wanted to find 1/2 q, nothing asked us to find 1/2 q, but if you wanted to find 1/2 q, you could do it like this. Watch this. 1/2 q is half each of these numbers, so it's 3, 1. Well, let's graph 3, 1. Look here. Let's graph 3, 1. This is just bonus stuff. 3 1s right there. Look at that. So it's the same vector, and if this was all done exactly technically correct, it should be laying directly on top of itself. So that's just my hand. But there's 1/2 q, which you may notice is half the length of q in the same direction because it's positive. Now I keep saying in the same correction. So what happens if you make it negative? Well, we have 2q up here is negative 12, negative 4, and we could indeed go out the same distance over here that we did negatively speaking. And if everything works out, and we have everything spaced just the same over here, just freehanding it, and we go do negative 11, negative 12, if we go do negative 2q in this orange, let's say, negative 2q in this orange, then we're going to go to negative 12, negative 4, and you may notice that if I do this right, and I put this exactly where this needs to go, and it doesn't screw up at the end, there we go, that it's twice the length of the original vector, except in the opposite direction. So it's exactly the same vector, just double the length, and in the opposite direction. So a negative version of the same vector is going to be the same vector, just in an opposite direction. For example, to find negative q, if you wanted to find negative vector q, then that's just going to be make each thing negative, so negative 6, negative 2. And if you wanted to find negative 6, negative 2, well, negative 6, negative 2 is going to be the same vector that just ends right here. That is negative q. It's the same vector, the same as the blue one up here, except it just goes in the opposite direction and terminates right here. That's all that negatives do to vectors. So that's pretty much everything that you need to know. We've already talked about the shrink from negative 1/3, and you can see here that all this is going to do is just flip it and shrink it by a factor of 1/3. And this is just going to scale it up by a factor of pi. Now, 6 pi is well off this grid here. It's 18, 19 something, and we only go to 12. But you get the idea of how to stretch and shrink these things using scalars. It's not a terribly complicated thing, and we'll get plenty of practice on it in class. And of course, if you've got any questions, ask me. Let me know. That's my job. All right, so just so much text, and I know that you guys just love walls of text. So go ahead and pause the video, get all this down, and then we'll talk about it. So the magnitude of a vector v, and v written in standard position. Now notice it has to be written in standard position. If it's not written in standard position, then get it in standard position using the very first thing we talked about. is written the magnitude of vector v, that is, we use absolute value signs, equals the square root of x squared plus y squared. And that should look incredibly familiar to you. That's straight out of the Pythagorean theorem, because this is all just right triangle stuff, which is why it's in trig. Note that sometimes we write the absolute value of b, which is read the magnitude of v. That's read the magnitude of v. If you're talking about the magnitude of a vector, that's the magnitude of v. And then we use two absolute value signs on either sign instead. It's the exact same thing, and they both mean the exact same thing. It's just the square root of the first component plus the square root of the second. It's the square of the first component plus the square of the second component, all under a square root. It's the exact same thing, and that's just a distance. They both just mean distance in a metric space. And if you want a ton of just deep lore reading on this, go read up on metric spaces. You can learn a thing or two. So the direction of a vector v is given by this. Theta is the arctan of y over x. That is, it's the inverse tangent of y over x. That is, the tangent of theta is y over x. We know that. So you just take the inverse tangent of both sides, and you get arctan of y over x, and that's going to give you your theta. Since we know x and y, since those are what's given to us, the distance that we ran, and then the distance that we rise rather, we know that the tangent is going to be the relationship between y and x, so of course that makes sense. Two vectors are equal if and only if they have the same magnitude and direction, or if they have the same position vector, either way. So if two vectors, you figure out that they have the same magnitude and direction, they're the same vector. If they both have the same position vector, they're the same vector. This magnitude and direction thing is kind of a dumb way to find equality, though, since all you have to do to find position vectors of vectors that don't start at the origin is just do some basic subtraction to get them back down to the origin in the first place, and then compare their position vectors. So I really genuinely don't know why you would ever need to do this, but, like, you know, it's true, so I'm going to say it. And then we have an example. We say find the magnitude and direction of a vector with initial point r 7, 0 and terminal point t being 6, negative 4. So notice that this is a vector, but it does not start at the origin. So it's usually a good idea to get it back to the origin. And if I can get rid of all of this annotation up here, I'll show you why. Because to talk about the magnitude of a vector, you need it written in standard position. That's what this is. This is standard position. This is assuming that you start at the origin. Notice that we do not start at the origin. So we just need to make it start at the origin. So let's not even bother with it in this current form. Let's just get it to be at the origin. So we know that our position vector is going to be the terminal points x, so 6, minus the initial points 7, comma, and then the terminal points negative 4, minus the initial points 0. This is the vector that we're actually talking about in standard position. So this vector will start at 0, 0. So this is the vector negative 1, negative 4. This is what we want to operate on. It's the exact same thing as working on the vector that starts here at r and ends at t, so vector rt. This is also vector rt. These are both vector rt. Except now we've just copied and pasted it. Well, we've copied it and we've moved it down to the origin is the only thing that we've done. And I'll actually show you that. So I'm going to write this up just so that you can see it, just in case it helps. So we start at r being 7, 0. We've got t being 6, negative 4. Okay, and then we've got the final vector to be negative 1, negative 4. So let's take a look at that, and let me show you what that is. And then we were asked to find the magnitude and direction of both of those. So we'll find the magnitude and direction of both of those easily enough. But let me show you this. So let me draw this vector. Let me draw RT here, and I'll draw it using the exact same color. So this vector starts at 7, 0. So it starts at 7, 0. So it starts over here at 7, 0. And then it goes to 6, negative 4. So it goes to 6, negative 4. So what we're dealing with is this vector right here. This right here is vector RT. Okay, so it started at 7, 0 right here, and it ended here at 6, negative 4. This right here is vector RT. Now, notice something. What I'm saying is that if we move it over here, that it's going to have terminal point here and starting point here. And if you don't believe me, just watch this. I'm just going to click on this thing, and I'm going to drag it over here. Watch this, if I can get it to work. I'm just going to drag it over here. That's all I'm going to do. And look, once I've drug it over here, it's the same vector, except it's in standard position. That is, it starts at 0, 0. It's the same vector. So we're talking about the same original vector. So keep that in mind. And then the only thing that we're wanting to do is figure out its magnitude and its direction. And that's incredibly easy math. So its magnitude, so the magnitude, we would write the magnitude, and this thing has a name, it's RT, so it's the magnitude of vector RT. And you can either write it like this, or you can get extra fancy if you don't like using absolute value like that. And that's just going to be equal to the square root of, and once it's in standard position like this, we're just going to use these numbers. So it's the square root of x squared plus y squared. So it's the square root of negative 1 squared plus negative 4 squared. So there we go. That's easy enough. So that's the square root of, well, negative 1 squared is 1 plus 16. So it must be the square root of 17. So that's its magnitude. It's the square root of 17. And all that we're saying is its magnitude is just the distance. It's just this distance right here on the plane. That distance is the square root of 17. And if you think about it that way, it should make sense. Look, its y was negative 4. That is, this was its y, was negative 4. Okay? And then its x, which I'll write in this blue, okay, it was just this, negative 1. And if you'll notice, what we've got here is a right triangle with side 1. In terms of total distance, I guess negative 1 if you want this here, negative 4 here. You plug all of that into the Pythagorean theorem, and when you solve for this side here, you have to take the square root, you get this formula, and everything pops out just like you'd think it would. So all that we're talking about is just that length. So let me get rid of all this extra stuff here. That's the picture that I want you to have in your head. That's the length of the vector. The magnitude is the length. And then in terms of this direction, what we want is this angle here that this thing forms with the positive x-axis. And that's going to be given to us via some very basic trig. So we've just got to do a little bit of math here, but what we're going to type in is the arctangent of y over x. So negative 4 over negative 1. Okay, or if you prefer, the inverse tangent of negative 4 over negative 1. They're exactly the same. Negative 1, I said. Negative 1, I said. Okay, they're the exact same thing. And this is going to be your theta, your angle, this angle here, theta. Now, you may have to do some work with it because you know that your results should be in quadrant 3 just because you've drawn the picture and you understand what's happening, or you understand that a negative occurs in quadrant 3, however you want to do it. So we know kind of what our answer should look like. It should be an answer in degrees. Between 180 and 270, 180 and 270, that part of the graph here in quadrant 3 is what we're looking for. And so I'll give you the answer in radians also, but let's type this thing into a calculator and figure out what, I guess, negative over negative is positive. So what we're actually just looking for is the arctangent of 4, positive 4. That's all that we're looking for. So let's slap that in a calculator and figure out what we get. So when we do that, we're going to get about 1.33 radians. So this is about 1.33 radians, which remember is unitless, so we don't write that down. Or that's about 75 if we're rounding to 2 decimal places, 96 degrees. That's what we get. So what this gives us is a reference angle. That's in quadrant 1. So the actual angle that we were given, this angle here, which I'll write in red, this angle here in red, it's giving us this part. Okay? But what we want is the whole thing. So we need to add in this extra 180 degrees is all that we need to do. So just draw it and figure out what you need to add in is the easiest way to do this. So 75.96 degrees isn't right. That would give you this thing up here. What we actually need is this thing down here. So we need the whole thing. This angle right here is what it gave you. It gave you that this is 75.96 with the negative x-axis. We want it with the positive x-axis coming all the way around. So we have to add 180 to it. So our final answer will be that theta equals, and then we're just going to add 180 to this. So throw that thing into a calculator, or I don't know, use basic math, and we'll figure out that that is very simply just 255.96. So 255.96 degrees, or if you wanted it in radians, you would just add pi to this. Just that's how you add 360, or you would add 3.14 to this. So if you wanted to add 3.14 to that, that actually adds really easy. So 3.14 is 4 point, wow, I just lost track of everything. 4.47 at 3, 1, and 4 to each of the numbers. Radians, if you prefer. If you need to take the pi out of it, there are ways to do that on Delta Math. But that's the sort of question that you get asked, and that's how you answer it. So just be mindful of what quadrant your answer's in terms of the angle, but the magnitude is always going to be just an abysmally simple calculation. It's just always going to be something like that. All right. And of course, if you ever got questions, hey, ask me. That's my job. All right. So we're getting down near the end here. We define the unit vectors as vector I being 1, 0, so that is 1 in the x, and vector j being 1 in the y. Using these, we can write vector v, which is xy, as a linear combination of unit vectors as this: x times vector I plus y times vector j. Oh wow, look at all that stuff. It's ridiculous. So look, here's how to do it. I comes before j, and x comes before y. That's how I remember them. By the way, yes, there is a vector k, and yes, it does correspond with the z-coordinate if you're in 3 dimensions. There's a vector w if you're in 4 dimensions. If you really want to look up quaternions, go for it. They're nuts. In fact, quaternions, which is a 4-dimensional vector, makes so little sense, even though it is totally how they work. It makes so little sense that the mathematician Lewis Carroll wrote Alice in Wonderland based on how crazy this vector math can work once you start getting into like 4 or higher dimensions. Anyway, this is unit vector stuff, and that may look really difficult. I'm using the word linear combination here, and that just means that I added together scalar multiples of things, but this is ridiculously easy. Let me just show you. So I want to write 4, 3 in terms of vector I and vector j. So that is 4i with a vector hat plus 3j plus a vector hat. That's it. That's all there is to it. And if you don't believe me, what this is saying, that's the answer. That's all that you have to write, okay? I'm going to show you what this means. So blue is all you have to write. I'm going to go on an odyssey here in orange. What this is doing is this is 4 times the vector I, which was 1, 0 in standard position, okay? Comma, not comma, plus 3 times the unit vector j, like this. Very clearly, when you multiply that in, that's going to be the vector 4, 0 plus the vector 0, 3. And then when you add those together, you're going to get the vector 4, 3, which is what you originally started out with. That's really what you're doing, but all that it is you just write this number times I plus this number times j. That's it. If this number was negative, you'd put a negative here. If this number were negative, you'd put a negative here, or you just write that as a minus instead. That's it. That's literally it. We'll do another one. We'll actually do 2 more. But they really are this easy. 0, 2. Couple of ways to write it. Some people will want you to write it 0i plus 2j. Some people will want you to write it 2j. You'll figure out which Delta Math wants if you have to do it, but if it's up to me, I'm fine with this. Some professors are fine with this. Just ask them if you're going to be doing vector stuff. Both of them are correct to me. All right. And then I want to talk about the last one here. Negative 1, 5 is just going to be, well, negative I. We don't have to write the 1. We've never had to write a 1 before. We don't have to write it now either. Plus 5j. That's it. That's how you write it, like that. So the negative 1's right here, but we normally still don't write 1's. So if I had to do the vector 0, well, let's do the vector 1, 1. You could actually just write that as I plus j. And if that were the vector 1, negative 1, you would write it as I minus vector j. And that would be completely fine. It always helps to write the 1's. It's never wrong to do that, but again, math has all these shortcuts.